So in number 17 of 3.5, we're asked to decide whether or not this set is a vector space. And we're assuming sort of the standard operations. Now, in order to be a vector space, there's a whole set of requirements that you need. You need those list of 10. But what often we could do to check things a lot quicker is to just really double check the closure. That's what I like to check first. So if we have two matrices, A and B, well, that's not right to plus, so A and B. If we want to see if it's closure, that's often where the mistakes would come in. So we would say, well, let's write it this way. If we can do some scalar times A plus some other scalar times B, would this also fit into the same set? So I guess the question is, would this also have to be a matrix with a determinant equal to 0? Now there's a couple ways you can approach this. So recalling any time that you need to prove something, you can either find a counterexample, right? That's one option. And in this case, that might be our easiest way to double check. So it's not guaranteed, for instance, that this new matrix, maybe we'll call it E, because we've used little c and d already. E doesn't necessarily have a determinant equal to 0. One way I might do that is if I pick a clever value for A and B, I can get a counterexample. So for instance, I could let A be the matrix 1, 1, 0, 0. This will have a 0 determinant. I could let B be the matrix 0, 0, I don't know, 5, 7, something like that. This would also have a 0 determinant, right? Since the determinant of this is these two times these two. But A plus B is this matrix 1, 1, 5, 7, and this one has a determinant of 2. So this is a counterexample where the determinant of A is equal to 0, the determinant of B is equal to 0, but the determinant of the addition of the two is not equal to 0. Other ways you could do this, if you didn't see the counterexample, you could write out the determinant of this matrix right here. And this one would actually be sufficient even to just let C and D be 1 to make it even easier. But if you do that, you'll find it's not necessary that it has to be 0 as well. And you could write it out in terms of, if you wanted to, this could be written in sort of your matrix form with all the elements written out. So A1, 1, because first row, first column, first row, second column, second row, first column, 2, 2, all right, plus D. And then you could take the determinants and add everything up. Oh, excuse me. So you would, for this one, add them up and then take the determinants in that order, and you will end up, right, with not having it equal to 0. All right, so this is not a vector space. And that's, the way I use it is that closure property, which is really sort of properties 1 and 2 of the definitions. All right, there we go. We're back. All right, another problem in this section that asks us to verify whether or not we have a vector space. Asks about the set. So this number, let's say 19 from 3.5. Set of all 3 by 3 upper triangular matrices. Upper triangular matrices. Let's switch this over. So these would be things that look like this. So say we have A, B, C, 0, D, E, 0, 0, F, right? So all matrices of this form. And so some question that you might ask is think about closure. You can verify the property. So it is closed because if we were to multiply it by some number, E, or we already have an E in there, I guess we call it G, it'd be still closed because then we would just have GA, GB, GC, right? So you'd have still numbers there and you wouldn't turn these lower elements to anything besides zeros. So this is still in our same space, right? And you could do, if we added two of them together, right, I could do the closure property right at the same time. If I add two of these sorts of matrices, I'm not going to change these zeros. So those zeros are going to stay 0 if I add them. You can go through the properties. Does it have a 0 element? Sure. Well, if the matrix is the 0, all zeros, this is technically upper triangular because sort of in a trivial sense that the lower L here is all zeros. And so going through piece by piece, we can find that yes, we will have a vector space.